Welcome to the second lecture on phase transformation, and in this particular lecture we are going to discuss mainly on the different kinds of heat treatment processes on steel. The objective of this lecture is we have to understand what is hardenability of steel. Then we'll see some of the special heat treatment processes like austempering, mar-tempering, tempered martensite in continuous cooling transformation diagram. We also see the mechanical properties. We'll see some of the other heat treatment processes like process annealing, stress relief annealing, food annealing, normalizing, spherodising, and we'll see some of the surface hardening processes like flame and induction hardening, some case hardening processes like carburizing, nitriding, carbonitriding, plasma pulse hardening, like this. In the first part on phase transformation, we have studied iron carbide diagram, and basically we have considered only one component along with iron was the carbon. So that was the plain carbon steel. But alloying elements other than carbon like chromium, manganese, nickel, tungsten, molybdenum, they also have a great role in the mechanical properties, or in other words in the transformation. Now in this particular lecture we want to see that what are the role of these alloying elements. The first one is definitely with the adding of the other alloying elements, hardenability of the material increases. What we mean by hardenability, that we learn, but basically the idea is that at a lower cooling rate it is possible to form martensite if the more and more alloying elements are added. Okay, so this is in short is what is hardenability. Another thing is that the C curves that we have seen in case of plain carbon steel, where perlite and the bainite transformation was actually overlapped, right? But when the alloying elements are added, you will find that perlite transformation and bainite transformation having different C curves. So the idea will be clear if you look at this picture. You can see that this is the perlite transformation start, and this dotted line indicates the perlite transformation end, whereas this line indicates the bainite transformation start, and this dotted line indicates bainite transformation ends. So when the alloying elements like nickel, chromium, molybdenum is added with steel, then you will find that they are not what you have observed probably in case of a plain carbon steel like this. Now you can see for the bainite transformation and perlite transformation to separate C curves, whereas in case of a plain carbon steel these two C curves actually merged, and separately we have not identified these two different transformation curve in case of plain carbon steel. This is the last point that we have discussed in the last slide. Another one was related to the hardenability, and hardenability is very much related to this point that if you compare with the plain carbon steel transformation curve and when the other alloying elements are added, then you can see the bainite nose in case of a plain carbon steel may be in the order of 1 second, whereas here you can see it is in the order of 1 minute. So the bainite nose has been shifted towards the right. So what is the advantage of this? It has a great advantage, because suppose you want to make a martensite transformation, because you want to make a very strong material. Okay, so in that case the cooling rate, you can see in case of a plain carbon steel, has to be very cooling rate should be very large. Otherwise what you find that the whole cross section will not be martensite. This is what is the problem. Whereas if the bainite nose is here, you can see even the cooling rate is slow, still you can get martensite. But if the cooling rate is like this, here in case of a plain carbon steel, you can see that paralytic transformation starts. So some portion will be paralytic and some portion will be martensite. So these are basically the problem when for the large castings. That means if the section is very large, some of the casting sections are very large, where and now if you are cooling this casting or heat treating this casting, then what will happen, the outer surface which will be in contact with the water will be having very high cooling rate, definitely. So maybe you are maintaining a cooling rate very high, so at the surface you may get martensite. But at the central region, if the distance is very large, the cross section is very large, then what will happen, the cooling rate definitely at the central region will be much less, because heat has to conduct up to this position. So at the surface you may find this kind of a curve for the similar cooling rate. So outer surface and the central region having different cooling rate, and definitely at the central region the cooling rate is smaller. So what will happen, maybe it is possible that this region some paralytic transformation will take place, here maybe some martensitic transformation takes place. So different kind of structure you may find. There will be chances of a huge thermal gradient, so that is why the residual stresses will be there, thermal cracking, the chances of thermal cracking will be there. So these are the problem. So that is why if the bainite nose somehow can be shifted towards the right, then you see if you are cooling, in that case you see both the surface and the central region are martensitic transformation occurs. So that is why these for large sections castings or some large section hardening process, it is required that a slower cooling rate can form martensite, and that is why it is required that bainite nose should be shifted towards the right, and that role actually done by the different alloying elements. Okay, so that point has been described in the second part, that the alloying elements move the nose of the triple T diagram to the right. This implies a slower cooling rate can employ to obtain martensite. Okay, that means it increases the hardenability. Remember, hardenability is not the hardness, but if you can produce the martensite the whole section, that means you can get the whole section will be of similar grade of hardness. Okay, so somehow for the same carbon percentage you will be in a better position. Okay, so this is what is the hardenability, and that hardenability can be increased by the addition of the alloying elements. Here basically this comparison has been done. Here you can see the plain carbon steel, here you can see the 4340, 434 indicates some other alloying elements are also there, and last two digit indicates the carbon percentage. So this is basically 0.4% carbon. Okay, so what is the definition of hardenability? Hardenability is a term that is used to describe the ability of an alloy to be hardened by formation of martensite as a result of a given heat treatment. So whether we can form martensite or not. Okay, how can the formation of martensite will be easier if the bainite nose is shifted towards the right. So hardenability can be increased by shifting the bainite nose towards the right. So hardenability is not hardness, which is the resistance to indentation. You know the definition of hardness is resistance to indentation. Rather, hardenability is a qualitative measure of the rate at which hardness drops off with a distance into the interior of the specimen as a result of diminished martensite content. That means if the cross section is very large, definitely the cooling rate will gradually slow down towards the center. So chances of getting martensite will be less and less if you go towards the center. So that is why it is required that you shift the bainite nose towards the right, such that you are getting a huge relaxation of the cooling rate, such that the whole section can be martensite. Okay, so if the hardenability is very large, that means the bainite nose is quite away from this, you are getting a lot of time to reduce the temperature. So rather slow cooling at the center can also produce martensite. Okay, so here this is a very familiar test to find out the hardenability curve of different materials. This is called jominy and quench test. Here you can see how the test is done. Initially, this is the sample, maybe made of certain specimen, and then what is done at the end, it is first heated to the austenitic region, and then what is done at one end, basically water is spread. That means you are quenching. As you move along the axis towards this direction, definitely the cooling rate is small. Here the cooling rate at this region, the cooling rate is maximum, and as you go towards the axis, the cooling rate will be slower, so hardness will be less, because this portion probably will be the martensite, this portion will be martensite. Gradually it will no longer be martensite, so hardness will gradually reduce. And if you plot that hardness after measuring in the Rockwell hardness testing machine, they along the axis at different points, then you will get a curve like this, which indicates, you see the x-axis indicates the distance from where it is the quenching or the nozzle is spraying the water. So this is the zero distance, hardness is maximum, and as you move away along the axis, gradually the hardness is decreasing. So different kinds of alloying elements. This one is for the plain carbon steel. You can see the hardness is reducing drastically, because it is expected that the martensite formation is not occurring. Cooling rate is gradually slowing down and the material becoming soft. Whereas when the alloying elements, more and more alloying elements are there, you can see the hardness can be recovered even after a large distance away from this end. Okay, so these are basically the hardenability curves, and it gives an idea about how hardenable a material is. Okay, so here you can see 4340 is very hardenable material. Okay, now we have seen the isothermal transformation diagram in the first part of the phase transformation lecture, where basically how we have got this curve. If you remember, the transformation curve actually we found from the experiment of how the transformation occurs, that initially nucleation, then growth occurs, and finally the transformation. And the whole process we have considered at a particular temperature, say 600 degrees centigrade. And then what we did, here the transformation starts, here transformation finish. So in this way we plot the locus at different isothermal process, and we got this locus for the starting and the finishing of that particular transformation. So this particular triviality diagram that we have seen in the earlier lecture was isothermal transformation diagram. That means the whole transformation is taking place at a constant temperature. But practically most of the heat treatment process is not done by isothermal transformation. Rather, those are done by continuous cooling transformation diagram. Okay, so continuous cooling means, suppose you have a sample, you have austenize it. Suppose you reach a temperature, say 850 degrees centigrade. Now you are cooling it. How you are cooling it? Suppose you keep it in the air. So if you keep it in the air, what will happen? Its temperature will gradually decrease. It is not that during the transformation temperature remains constant. So temperature will gradually decrease from 850 to some up to room temperature. So the actually cooling curve will be like this. The temperature will gradually decrease. The cooling curve will not be like this. It will no longer be isothermal. So simple air cooling is an example which is not a isothermal cooling, which is rather a continuous cooling. Okay, so because the cooling is continuous. So if the practical process is continuous cooling, so obviously we have to refer the continuous cooling transformation diagram, how they are different from the isothermal transformation diagram. They are almost similar, but a slight change is there. You can see these lines, that means the solid lines you can see is the continuous cooling curves, whereas the dotted lines are the isothermal lines. Okay, so you can see that continuous lines are here, starting line, and this is the finishing line, and isothermal lines, this is the isothermal line, this is the starting, and this one is the finishing. Okay, and why continuous cooling curves is a bit starting is late and finishing is late, that you can understand that since the temperature is gradually decreasing, then what is happening, the starting will be at late, but since by the time of the transformation completes, the temperature is quite low, it is possible that the transformation will take place at a later time. Rather, if you can maintain the temperature at the higher level, then the transformation will occur earlier. So this is what is going to happen in case of continuous cooling transformation. So the curve is actually different from the triple T isothermal diagram. Now you can see some of the processes. Here you can see that a process which is a slow cooling process. That means suppose you have austenized steel. Let us consider a plain carbon steel. If you have austenized it and now you are cooling it very slowly. So what is the nature of cooling here? The nature of cooling may be you are doing it furnace cooling. What do you mean by the furnace cooling? Furnace cooling means suppose within a furnace you have kept the sample and you reach the temperature say 740 degrees centigrade, and after reaching that temperature, what you have done, you just switch off the furnace. If you switch off the furnace, then what will happen? Obviously the heating process will stop, but you are not taking out this sample out of the furnace. You keep that sample within the furnace to cool. So definitely the cooling process will be very slow. Okay, so in this way, if you cool, then the process is called furnace cooling. Okay, and by this furnace cooling, what will happen? The cooling rate that you are getting, that means from that 740 degrees centigrade to room temperature, it will take a long time. Okay, so it's a very slow cooling rate, and this process is called full annealing. This process is called full annealing process. And since the cooling rate is very slow, the curve may be like this, the blue one, and you can see the paralitic start and paralitic finish. So the structure that you are going to get is the coarse perlite, because it is the initial region. So coarse perlite you will get. Now if the cooling rate is bit higher, how can you do that? Same thing, but now instead of a furnace cooling, you just take the sample out of the furnace and keep it on air to cool it. So this is called air cooling. Okay, so here it is the air cooling, maybe. Here it is the furnace cooling, So if you do the air cooling, then what will happen? You will get the fine perlite, because paralitic start will be here, paralitic finish will be here. So this is a fine perlite that you will observe. Okay, so this process is called full annealing, and the air cooling, this process is called normalizing. So we have seen two important processes. One is full annealing, which is done by the furnace cooling. Remember, this is a continuous cooling process. This is not an isothermal cooling process. So the referred graphs are the continuous cooling transformation diagram. In case of normalizing, what we do? The cooling is air cooling. That means after reaching austenizing temperature, then you keep the sample out of the furnace into the open atmosphere to cool to room temperature. So it's a air cooling, and this process is called normalizing. What kind of structure you will get? You will get fine perlite. Clear? But in this way, if you see, it is not possible because if you draw the complete diagram, it will be like this. So however you cool, it is not possible to form the bainite, because now we are doing the continuous cooling kind of a thing. It is not possible to bainite transformation. Maybe bainite transformation is possible by this kind of isothermal thing, but by continuous cooling you cannot get bainite out of plain carbon steel. Very much you can get bainite from the alloy steel, because in that case bainitic transformation curve and the paralitic transformation curves are different. So in that case, by continuous cooling also you can get bainite, but in plain carbon steel you do not get it. Clear? Here you can see, you can get some idea about the cooling rate, where it is 35 degree centigrade per second, and if the cooling rate is less than that, then either you get the normalized steel or the annealed steel. But if it is more than 140 degree centigrade per second, then what you are going to get is the martensite. And if it is in between 35 degree and 140 degree centigrade, then you get both pearlite and martensite. Okay. And if your cooling rate is very high like this, then what structure you get? You get martensite. Okay, because the pearlitic transformation will be suppressed and you will get only martensite. And this particular cooling rate you can achieve by water quenching or water cooling. Simply put that sample out of the furnace and put it into the water, and this process is called quenching or hardening. What structure you get? You get martensitic structure. Clear? So here you can see I have told you that if it is not a plain carbon steel, if it is alloy steel, in that case you may get the bainitic structure also in between. Okay, and for other different cooling rates you can get this kind of different structures. Okay, now tempering is a very important process that is done after martensite transformation has occurred. So suppose we want to make a material very strong, so general tendency is what? We first austenize it, we first austenize the steel, and then we quench it. That means water quenching. By water quenching we form martensite, but that martensite is very brittle and not suitable for different machine components or different parts, structural parts, and that is why some amount of ductility is required to be imparted so that they become tough. So to impart this toughness, what is done? They are further heated to a temperature around say at 400 500 degrees centigrade and keep at that temperature for some time. Depending upon at which temperature you are heating and how long you are maintaining at that temperature, the new structure that is going to form in the martensite depends that how much mechanical properties you are going to change. So remember what is going to happen in case of martensite. Basically you are cooling it so fast, you have cooled it so fast, then carbon actually has not got any time to diffuse out of the structure. Okay, that's why when you are further heating during the tempering process, you are basically allowing some heat, and since you are keeping it for a long time at that temperature, then what happens that those carbon then easily diffuse out of the structure, martensitic structure, and they form this kind of a spherical particles within the martensitic structure. So martensite, the whole structure is martensite, and within that some spherical structures you will get. These are basically the cementite ball kind of a structure you will observe. Okay, this particular structure you will get in case of tempered martensite. Okay, and definitely because of that certain amount of toughness will be definitely increase, but the strength definitely will decrease a bit. Okay, and how much ductility you want to impart, that depends upon how much temperature or how long you are staying at that temperature, because the diffusion process will dictate that. Here you can see the different temperature microstructure of the tempered martensite. Here you can see this is the structure of the martensite, where basically needle-like, this kind of a needle-like structures you will observe, where carbon actually trapped within the structure, actually not diffused out, diffusionless kind of a transformation occurs. Now when you are heating and allowing some time, then what happens, some of the carbide particles will come out of the structure, and some amount of toughness or ductility will be increased, and this structure is called troosite at a temperature maybe 300 or something like that. If the temperature is say 400 to 500 degrees centigrade, maybe you will get this kind of a sorbite structure where you can see more number of spherical particles are present. Okay, so at a higher temperature, keeping for a long time, you will get this sorbitic structure. And if you further increase, and if the temperature is around 700 650 degrees centigrade, then and keep it for a long time, you will get this kind of small spherical structures throughout the material, and which is nothing but the spherodite. Okay, and you can see their Brinell hardness number, so you can get some idea about how the hardness is sacrificed, but some toughness is definitely increasing. So this one is highly machinable and softest kind of material, even softer than the coarse perlite. Whereas martensite is very hard, not suitable for the application, and that is why these structures are basically preferred. So tempered martensites are used for all practical purposes. Here you can see with the increase of temperature of the tempering, you can see the strength is gradually decreasing. Okay, strength is gradually decreasing. So here is the process of quenching has been shown in detail, where you can see practically, since you are cooling it very fast, it is possible that outer surface the cooling rate is very high, so will form martensite first, and the inner portion will still be austenite. Then what will happen actually, when this austenite will try to convert it into martensite, they will give pressure to the martensite, so the martensite will be under, outer surface martensite will be under tension, whereas the inside austenite will be under compression. So in this way the residual stresses will be developed within the material, and because of the tension in the martensite, there is a chance of the formation of crack at the surface, and this is what is called the quench crack. So this is a dangerous problem that happened during the quenching. So many times it has been observed that during quenching the quench crack occurs and the material fails. To avoid this kind of quenching crack, what is done, that the process is called the mar-tempering. It is not that it is completely, so before martensitic start temperature, it is cooled very fast, then allowed certain time, so that what happens, the temperature gradient that was developed between the center and the surface, you know, the surface, at the surface what will happen, so the cooling rate is very high, so curve will be like this. At the center definitely the cooling rate will be small, the curve will be like this, so there will be huge temperature gradient. So what is done, before just coming before the martensitic start temperature, it is some time is allowed, but the time should not be such that the bainitic transformation starts. It should be before the bainitic transformation. So then what will happen, this thermal gradient will no longer be there, and chances of the thermal cracking will be less, and then it is cooled to the room temperature. So in that case, the chances of this kind of residual stresses or the chances of the quench crack will be reduced. So the important point is that chances of thermal shock during quenching or the distortion, minimize cracking, these are the important properties. But definitely some impact toughness may increase because of this, because there is no residual stresses or no fracture surfaces or the cracks produced within the material, so obviously the impact toughness will be better. Another special kind of a heat treatment process is the austempering, where what is done, that in this case you can see basically bainitic transformation is done. So initially it is quenched very fast, and then keep it for a long time before martensitic start, and the allowed for the bainitic transformation. So in this way the bainite can be transformed in case of plain carbon steel. Okay, so this particular process is called the austempering. What is the microstructure of the austempering? It is the bainite microstructure. So what is bainite microstructure? Already you know, the bainite microstructure is basically within a ferrite matrix, a needle like kind of a carbides are settled. Okay, very fine structures, so hardness is very high, even harder than the fine perlite. And For this kind of a isothermal transformation, generally salt bath is used, and here you can see around 150 to 450 degrees centigrade this salt bath is used, and at that salt bath basically the sample is kept for a long time so that the bainitic transformation completed. So here you can see that we have understood that martensite is a very strong or a very hard material, but martensite depends on the carbon percent present in that particular component. If the carbon percentage is very low, then the martensite that will form in that low carbon steel will have lower hardness. But if the carbon percentage is high in the sample and then you form the martensite, definitely its hardness will be high. Okay, here there is a comparison of the hardness of the different structure that we get during heat treatment. Coarse pearlite, how we get coarse pearlite? By the full annealing. By full annealing we get coarse pearlite. Full annealing how we can achieve? By furnace cooling. How can we get fine pearlite? Fine pearlite we get by normalizing process. How normalizing is achieved? By air cooling. Okay, bainitic transformation. How bainitic transformation is done? By austempering. By austempering. And how austempering is achieved? Initially quenching before martensitic start, and then at a salt bath we have done it. Martensitic by quenching. Okay, so finally the tempering process. So further it is heated in the furnace after quenching. So first quenching and then heated in the furnace. So here you can see the hardness is changing, and hardness at different temperatures. So you get some idea that gradually the hardness is increasing as you go down. Now you see the mechanical properties. You can get some idea by the time that obviously if the composition of carbon increases, then definitely the tensile strength will increase, the hardness will increase, yield strength will increase. Whereas if the composition of carbon increases, okay, then you find that impact energy or the isothermal impact energy will reduce, or the impact toughness will reduce. Okay, now ductility will be reduced. Ductility can be measured in terms of reduction in area or the percentage elongation. You can see the ductility will be reduced with the increase of carbon percentage. So here you can see the comparison of the fine pearlite. In case of a fine pearlite, percentage of composition of carbon. In case of fine pearlite, you see the hardness is high, whereas coarse pearlite hardness is less. In case of spherodite, hardness is even less. Okay, so this is the softest grade that you can see. Here you can see the ductility, and the ductility in case of fine pearlite is very small, coarse pearlite, and ductility is very high in case of spherodite, and that is why this particular structure is suitable for machining. So for very hard materials it's sometimes difficult for the machining. Then what is done? By heat treatment they have spherodite structure is formed, and then machining is done, and then again by the heat treatment they are made hard. Okay, so these are the basically processes. So spherodite structure helps in machining because they are the softest grade. Here you can see again with the composition, the martensite, the hardness of the martensite also depends on the carbon composition, and fine pearlite and the tempered martensite also in a similar manner. So here is a comparison table. You just go through it, you will get the things that we have just discussed for different kinds of structure. Okay, what are the arrangement of phases and their mechanical properties. Now coming to the different grades of steel, we have seen that they have nomenclature like 1040, 1080. This 10 indicates the plain carbon steel. Plain carbon steel means mainly carbon is there along with iron, and some percentage of manganese is always there. Okay, and the last two digit 8040 indicates the percentage of carbon. 80 indicates 0.8% carbon. Okay, 40 indicates 0.4% carbon. Okay, and here you can see 4340 steel you have seen many times. 4340, here you can see what are the composition, what are the different components present in 4340 steel. This is an alloy steel. Many other components are present along with iron and carbon. So here the processes has been shown. The continuous cooling curves. Here you can see the full annealing. You will get the coarse perlite. Remember, these are very important. By normalizing, means air cooling, you will get fine perlite. By while quenching, some amount will be perlite and the remaining portion will be martensite. By while quenching, and the cooling rate is highest in case of water quenching, you will get martensite. Even the brine quenching is also done, and the cooling rate is even faster. Okay, and you will get martensite definitely. Okay, so cooling rates are also given here, so you will get some idea about the cooling rates in different processes. Now coming to the heat treatment processes in steels, these are the actual ranges at which the temperature is first attained, and then after that how the annealing, normalizing or other heat treatment processes are done. This is a very important guideline. Okay, and for the hypoeutectoid and for the hypereutectoid, they are different. Okay, here you can see, probably you remember this particular portion of the iron carbon diagram, eutectoid point, and you have seen probably this temperature is called A3 temperature. Eutectoid temperature is called A1 temperature. Okay, and this particular temperature line is called the ACM temperature. Okay, what are these things? A1, this one is called the lower critical temperature. A1, the eutectoid temperature is called lower critical temperature. A3 temperature is called upper critical temperature for the hypoeutectoid steel, that means which are in this region. Hypoeutectoid steel, this is the upper critical temperature, A3. And what is ACM? ACM is also upper critical temperature for the hypereutectoid steel. Okay, these things you have to remember. Now suppose you want to do the full annealing process. The first question is, in furnace, what is the initial temperature that you will raise? And that depends on the carbon percentage. Okay, suppose your carbon percentage is 0.4. That means it is a hypoeutectoid steel. And for hypoeutectoid steel, initially how much temperature you will reach? The guideline is, for full annealing process, you have, for the hypoeutectoid steel, you have, this is the upper critical temperature, this one is the lower critical temperature. Lower critical temperature is nothing but the eutectoid temperature. Now see, above the upper critical temperature, you see, for the full annealing, above the upper critical temperature you have to maintain 30 degrees centigrade. So initially you have to heat it above upper critical temperature up to 30 degrees centigrade. So 30 degrees centigrade more than the upper critical temperature. So what you have to do? You have to go to the iron carbon diagram. In the iron carbon diagram, corresponding to the carbon percentage of that steel, you have to see what is the value of A3. If you find that your A3 is this temperature, so simply add 30 degrees centigrade with it. So that will be the temperature that you have to reach before annealing. Then from that temperature, basically you have to do the furnace cooling or the annealing process. Okay, if your steel is not hypoeutectoid steel, but your steel is a hypereutectoid steel, say the carbon percentage is 1%, then what is the guideline for the full annealing process? Then guideline for the full annealing process, you see, for the hypereutectoid steel, this is the annealing process, you have to go about 30 degrees centigrade than the lower critical temperature. See, now for the hypereutectoid steel, you need not to go above upper critical, you have to go only the lower critical temperature by 30 degrees centigrade, and then you have to cool for the annealing process. Okay, so basically the range is like this for the annealing: 30 degrees centigrade, 30 degrees centigrade for the above the upper critical temperature for the hypoeutectoid, and 30 degrees centigrade above the lower critical temperature for the hypereutectoid steel. Clear? So this is what is the guideline for the full annealing. and this is also the guideline for the hardening or quenching process. Okay, now coming to the normalizing process. In normalizing process, initially again you have to do the austenizing. So for the normalizing process, you see initially you have to heat 55 degrees centigrade above the upper critical temperature for the hypoeutectoid steel and 55 degrees centigrade above the upper critical temperature of the hypereutectoid steel also. So in both cases, hypoeutectoid or hypereutectoid, for the normalizing process you have to heat initially above the upper critical temperature by 55 degrees centigrade. So the graph is something like this. So it is 55 degrees centigrade above this temperature. In both cases it is above the upper critical temperature, and then you have to cool in air for the normalizing process as usual. Now you have understood the full annealing process, normalizing process, quenching process. Quenching guideline is same as the annealing, full annealing guideline. Okay, now another process is there, which is called the process annealing process. Process annealing is not the full annealing, and you can see the temperature range is below the eutectoid temperature or the lower critical temperature. Okay, and another process you see the spherodising annealing, and this process is also below the lower critical temperature. Okay, so but spherodising annealing is done for the steel having carbon percentage generally higher than 0.6. Here you can see the carbon percentage is 0.6. So if the carbon percentage is less than 0.6, generally spherodising annealing is not done. Spherodising annealing is done if the carbon percentage is very high, because if the carbon percentage is very high, then only it is required that you have to make it soft, and that is why the spherodized annealing process is done. Okay, so the guideline here has been shown for the process annealing. You see the temperature, you have to heat the sample at a temperature 80 to 170 degrees centigrade below the lower critical temperature. So this is what is the guideline for the hypoeutectoid steel process annealing. For the hypereutectoid steel, spherodizing is possible, and that temperature is what? 30 degrees centigrade below lower critical temperature. Okay, so spherodizing is not done in the hypoeutectoid steel generally. It is done in the hypereutectoid steel. It is 30 degrees centigrade below the lower critical temperature, and the process annealing is generally done for the very low carbon steels. Okay, that is not done in case of hypereutectoid steel. Okay, generally carbon percentage is less than 0.2%. In those cases, basically process annealing is done. Okay, and the temperature range in which it is done is below 80 to 70 degrees centigrade than the lower critical temperature. Now process annealing, this thing we'll see in detail, that this annealing process in which the metal is heated above the registration temperature for enough time, then cooling is done in air up to the room temperature. Okay, we'll understand this process. Actually there are three stages in the process annealing process: the recovery, recrystallization, and grain growth. This process is generally done during the cold working process, like forging process you are doing. That means you are changing the shape of the material. When you are hammering or something way by which you are doing some kind of a plastic deformation in the material, what happens? Material becomes very hard. Material becomes very hard because of the strain that is generated. Okay, that is what is called the strain hardening, work hardening, or the cold working. If you do this kind of thing, then what happens? That within the material, lot of dislocations are accumulated within the grains, and that is why it becomes very hard, and lot of stresses basically created within the material, and that is why there is a chance of cracking those material. So for that, what is done? Initially the material is heated. So initially, because of cold working, what happens? Material is strained. Because of that, a lot of dislocation lines produces, and those dislocations basically make the material more and more hard. So because of plastic deformation, basically hardness increases. This process is called strain hardening or word hardening. And to relieve these stresses, initially material is heated, and this initial heating at a low temperature, maybe 250-300 degrees centigrade, is called the recovery. So recovery is the process by which the deformed grains, that means by plastic deformation, by deformed grains can reduce their stored energy by removal of the rearrangement of defects in their crystal structure. So what is done basically in the recovery process, because of heating, some of the point defects get out of the crystal, some of the dislocations get out of the crystal, but many dislocations are still present, but those dislocations are basically rearranged into this kind of a structure, where these are the accumulation of the dislocation, maybe around this small structure. So this kind of thing occurs in recovery. Recovery is a kind of rearrangement process of the dislocation structures, but dislocations are still there at a very high amount. Okay, so it occurs, but the main objective of the recovery process is that stress relieving. Lot of stress can be removed because of that. Okay, internal stresses can be relieved. So recovery occurs at a lower temperature stage of all annealing processes and before appearance of new strain-free grains. So what is the next stage? Next stage is the recrystallization. In the recrystallization, what happens? I have told you that the rearrangement of the grains occurs, but still the dislocations are present. Now in the recrystallization process, what happens? From the dislocation grains, new small grains nucleates, those are dislocation free. So what is the process? Process is basically the grains with dislocation is transformed into dislocation free grains or the strain free grains. Okay, so this process is a kind of a transformation, is called recrystallization. Okay, so recrystallization process is what? Dislocation grain with dislocation is transformed into dislocation free grains. Okay, the process is exactly similar how the general transformation occurs, like nucleation and growth. So in this stage, new strain free grains nucleates and grow to replace the deformed by internal stresses. So if annealing is allowed to continue once recrystallization has completed, then the grain growth occurs. So the next stage is what? Next stage, the small strain-free grains, those has been formed because of the recrystallization. Now those are gradually coarsened, or their size actually increases, and this process is what is called grain growth. Definitely with the grain growth, the strength of the material decreases. Okay, so the initial process, initially after the cold work or the plastic deformation, we do the annealing, the process annealing, which having three different stages. Initially the recovery is the driving force, is the free energy stored in the point defects and the dislocation, because point defects and dislocations are basically the defects in the material having the higher free energy. So they are oriented in a different fashion so that the free energy decreases and point defects get out of the crystal. Some of the point defects get out of the crystal, so definitely free energy will decrease. So recovery occurs initially. After that, recrystallization occurs. Recrystallization is a process where strain grains or the with dislocation grains converted into strain free grains. That means definitely these having the higher free energy because they are the defects, and now the defect free grains are created, so definitely the free energy will decrease. So that is where recrystallization occurs. So here this is the driving force, that's why this occurs. And why the grain growth occurs? Obviously driving force is the free energy stored in the grain boundaries. Grain boundaries are the defective region. If there are small grains, then lot of grain boundaries are there. If there are large grains, only small grain boundary is there. So that is why the free energy will decrease. So that is why the grain growth occurs. So combination of all these three processes is what is the process annealing. Here this is shown. Here you can see lot of small grain dislocations are present within the material. But after recovery stage, you can see those are reoriented into small groups where the dislocations as if concentrated in this region, but dislocations are still there. Then recrystallization starts. Now dislocation free grains are started to create. They are nucleating, they are growing, and this process is called recrystallization. And finally it is fully recrystallized, fully strain free grains produces, and then the grain growth. They are coarsened and produces this kind of a grain growth. Okay, so these are the processes, how process annealing done. What about the mechanical properties? Definitely after plastic deformation, you know, the hardness increases, and gradually after recovery, recrystallization and grain growth, its hardness is gradually decreasing. On the other hand, ductility, you can see ductility is gradually increasing. Here also you can see the different types of heat treatment in steel that happens. We have seen how their mechanical properties and their ranges. Okay. Now we'll see surface hardening processes. Okay. Many times it is required that hard surface are required because the component that is made to resist wear and tear at the surfaces, whereas we need a tough core to resist the shock loads. Okay, so this kind of requirement you can think of a gear, where gear with when they are mating with the other gears, the only wear and tear that is happening only at the surface, but the core is, we do not need the core to be very hard. Rather, for the to resist shock loads, we need rather softer, tough core. Okay, so only the surface is required to be hard, not the whole material. In many components, such requirements are there, like bearings, because in the bearing also the surface which is coming in wear and tear, and that is why to resist it we need the high hardness only at the surface, not the whole material. And similarly, you know, in case of a fatigue loading when is coming, it is the surface where from the cracks created and then that propagate. So surface to be very hard, then the crack will not form at the surface. So this kind of surface hardening is very important. This surface hardening can be of two kinds in general. One is the selective heating of the surface layers, another one is the case hardening. So first we will see the selective heating of the surface layers. The first you can see here, it is the flame hardening. Flame hardening is a selective heating process where initially with the help of oxyacetylene flame we can heat up to 850 degrees centigrade a portion, and then with the help of water we can quench it. Then what will happen, that the outer surface will become martensite and become very hard, not the whole material. So with the help of oxyacetylene gas we can heat the surface to a very high temperature around 850 and then quench with the water, so we can form the martensite at the outer surface only. So this is a very useful technique. Where this is done, depth of the hardening depends on the rate of heat supply, at which rate we are supplying the heat. And the flame hardening is mostly used in case of carbon alloys steels, where the carbon content is between 0.4 to 0.6%, where they are used shafts, gears, cylinder liners, crankshafts, okay, bearing journals, different applications are there. You can see one of such processes like flame hardening is done in case of gears. Here you can see with the help of oxyacetylene gas, basically outer surface of the gear piece, which will require to be very hard because same in the base is hard. And after taking a temperature, you see that water quenching is done. Okay, so this is the process by which we can do the surface can be hardened only. and this process is one of the selectivity called flame hardening. Okay. Sorry. Now coming to the another kind of selectivity, which is called the induction hardening. In case of induction hardening, what is done basically with the help of AC current source through a coil, some magnetic field is created, and that magnetic field ultimately produces eddy currents within the sample, and by changing the frequency it is possible to control the heating process. Okay, so this is what is the induction hardening. The same principle what is done in normal induction heater, and this very high control is possible by the induction heating, and if you see you will understand it.
Show you. So here I have a handheld transformer fitted to quite a smart pistol grip. We're going to use this known smart way just by turning the power on with the trigger, and fitted here is a single turn coil, encircling coil, and we're going to run a high frequency current through the surface of the part giving us heat. So here we go.
So
as you can see, I can put in heat exactly where I need it. I'm not getting hot, this stays cold, and it's very efficient. In fact, with our equipment, this is carbon steel by the way, a solid bar. With our equipment we even have low voltage on the coil. So if you did happen to touch the coil, it would be quite safe. How is this? The workpiece is placed in the coil.
So you can see the attachment like cooling arrangement is also there, so that after heating the quenching also can be done and it can be heated.
It's placed around or adjacent to the workpiece. It does not touch the workpiece, and heat is only generated by the induced current flowing in the workpiece. Correctly designed, made and maintained coil is crucial to the outcome of any induction.
So you have understood how through the induction hardening process also the material can be hardened, and then quenching at the surface will produce the hardness at the surface. Okay, and you can see the temperature is in between 850 to 1000 degrees centigrade. Okay, and by cooling it is possible to form martensite at the surface. Okay, and the most important thing, remember the high frequency AC current, which is the source. If the frequency is very high, then the depth of hardness will be low. So less will be the hardened depth if the frequency is very high, and the reverse thing occurs if the frequency is low. Now let us see another kind of surface hardening process, which is called the carburizing. In the carburizing process, the idea is that around the sample that we want to hard only at the surface is a carbon environment is created, either in the form of solid charcoal or in the form of some hydrocarbon gas, whatever that may be. So some environment that is created that is having the carbon atoms. Then if you heat it at a very high temperature, then what happens, this carbon will diffuse into the material, and definitely the carbon content of that steel should be less than the environment that you are creating. Obviously the carbon environment will having the higher carbon percentage, so that is why the carbon will now diffuse within the material. And how long you are heating in the furnace with this environment will dictate that what will be the depth of the carbon that is penetrating. Okay, so this method is what is called the carburizing process. Okay, so it can be solid carburizers can be used, or the gas carburization can be done with the help of gaseous hydrocarbon. Okay, so here the fundamental equations, you can see the charcoal react with oxygen, produces CO, and barium carbonate is also used, so that carbon monoxide is also prepared, because this carbon monoxide dissociates into carbon atoms, and these carbon atoms are going to diffuse within the material. The charcoal will not directly go into the material, but after this reaction the carbon atoms that will be produced will diffuse within the material. Okay, so this is what is the reactions that is taking place within the furnace. Okay, in case of gas carburization, I have told you some hydrocarbons are used, maybe methane, butane, or some other kinds of hydrocarbons may be possible, and by dissociation again carbon can be produced, or some producer gas having carbon monoxide can also be used to produce the carbon atoms. These carbon atoms ultimately diffuse and case harden, and this is the hardness depth is called the case depth. Okay, so that is why this is called the case hardening. Case means the depth up to which hardness will be maintained. Okay, so this is a process that is done generally steel containing less than 0.2% carbon. Okay, and it is possible that hardness can be increased, or carbon can be increased up to 1% approximately. Here which is followed by quenching process in case of gas carburization, or in case of solid carburization, whatever that may be. After that heat treatment is done, that means the quenching and tempering can be done. So because martensite or the tempered martensite is produced, so this is what is the plan. You can see this is within the furnace, this is kept. If you want to see, you can also see there. In fact, carburization.
I'm Ann. And I'm Todd. One of the most common projects for machinist apprentices in steel, so that they're more wear resistant.
So here you can see the charcoal powders are packing in a box.
Lay down about an inch of carbonaceous material in a steel box with a tight-fitting lid. Yes, we really are using broken up charcoal briquettes, because it actually works by at least 1 inch. Put the lid on top of the box and fill in any gap in 18 steel scraps, so we can test the hardness later without putting
further it is filled with the charcoal.
Rising. Pack carburizing.
Then it is packed within the box, put it into the furnace. You can see the temperature.
We'll leave the box in the furnace to carburize for 8 hours.
It's around 8 hours.
Since we've got some time to kill, let's measure the hardness of a piece of untreated 1018 and tip will penetrate deeper into the surface of softer materials than harder materials. A higher number on the Rockwell C scale indicates a harder material, with the scale topping out at 1. But inside the furnace, there's a bit of science magic happening. Carbon-rich gas comes in contact with the metal surface, breaks down, and some amount of free carbon is dissolved into the hot steel. Time, temperature, and the composition of the atmosphere all affect the rate at which carbon is absorbed and how deeply it penetrates into the steel. After 8 hours at 1700 degrees, the carbon should penetrate 1/16 of an inch into the part. After letting the parts cool in the furnace overnight, it's time to take them out. surface layer called a case. Turn the heat up to 1450 degrees Fahrenheit.
So after this,
and then put the parts back into the furnace.
So for quenching, the parts is again heated into the furnace.
We only need to get the parts up to temperature, so 10 to 15 minutes should do the trick. At room temperature, the microscopic structure of the high-carbon steel is composed of alternating layers of iron and brittle iron carbide. This microstructure is known as perlite. When the steel gets hot enough, the perlite dissolves, and the microstructure transforms into a non-magnetic solution of carbon and iron called austenite. Once all of the perlite is dissolved, it's time to quench. Pull the parts out with a set of tongs. Quickly plunge them into a container of water and agitate the parts in a figure-8 motion until they're cool to the touch. Because we're cooling the steel so rapidly, the austenite won't have enough time to separate back out into iron and iron carbide. The resulting steel microstructure, called martensite, is composed of needle-like shards of iron supersaturated with carbon. Parts by heating them back up to a relatively low temperature and holding them at that point for some amount of time. So let's go ahead and heat up the draw furnace to 400 degrees Fahrenheit. Place the parts in the basket and lower them down into the furnace. Make sure to replace the lid. By the way, this part of the process is called tempering or drawing. Remove the parts and let them air cool at room temperature. Don't go dunking them in water at this point.
So you can see this is the whole carburizing process, how it happens. Now in case of a gas carburizing, you can see this process. So here is some gaseous environment present, and here you can see the sample, and after the gas carburization process, it is required to be quenching. So part is taken out and it is deep into the water for the quenching process.
It's normal to lose a...
Sorry. Now comparison of the solid and the gas carburizing, if you do that, the process of gas carburizing occurs more quickly and almost no time is required actually for heating the carburizing box, and that is why it is more effective in that sense. Gas carburizing can also be more easily controlled and automatized. Hardness achieved. You can see the hardness can be achieved from 200 HB. It is possible to convert it to around 750 HB. Application. This process is usually carried out on a steel containing less than 0.2% carbon, and carburizing is usually employed for treating certain types of machine elements like gear wheels, okay, shaft pins, camshafts, cam worms, etc. Now, another case hardening process which is called the nitriding, and this is the process of diffusion saturation of steel surface with nitrogen, and the component is heated in a mixture of ammonia and nitrogen, so that nitrogen diffuses into the surface layers and hard nitride compounds are formed. Okay, the applications you can see: crankshaft, cylinder sleeves, worm gears, like that. Okay, so in the carburizing process, it is the carbon atom that diffuses. In case of nitriding, it is basically the nitrogen atom that is diffusing and forming the strong nitrides, and the surface becomes very hard. Now, in the process, remember one thing, that before nitriding process, you have to do all the heat treatment, because after nitriding, there is no required of quenching and all that. So all the heat treatment process is to be done before nitriding, and after nitriding, it is basically the surface finishing operation that is done. In the nitriding process, component is heated in a mixture of ammonia and hard nitride compounds are formed. Okay, and it is the temperature you can see 5 to 600 degrees centigrade, which is quite low if you compare with respect to carburizing processes. This process is used with those steels, those alloys of steels which contains elements that form stable nitride. So along with the plain carbon steel, if you add these alloying elements, that will help in forming the nitrides, because they are strong nitride formers. Okay, the main disadvantage is that it takes a very long time, around 100 hours you have to keep it at that temperature, 500 to 600 degree centigrades. Okay, so here you can see the process where the ammonia and nitrogen, that is basically the gas that is fed into the that is creating the environment around that sample, where the heater is there, and obviously some argon gas is passed to create neutral environment so that oxygen cannot come into it. Okay, so if you want to see the process, you can see. So basically, these are the samples which kept within that environment. You can see this is basically the heater, liners are there, and it is kept for a very long time for completing the process. Okay. Now the depth to which the nitrides are formed depends on the temperature and the time, but you see unlikely to exceed 0.7 millimeters. So the depth that is up to which the hardness is produced is very, very small if you compare with respect to the carburizing process. Okay, and the components are cooled slowly in the ammonia hydrogen atmosphere. The nitrogen diffusion decreases with an increase of the carbon component. So the steel, if the carbon content is very high in that steel, then the nitrogen diffusion decreases. Okay, and with the increase of the carbon content, the formation of carbonitride phase becomes possible. What are the other comparison we can make with the carburizing process? Obviously nitriding is a time consuming process. Higher values of hardness and wear resistance can be produced by nitriding. That is a very important point. And not only that, cracking and distortions are less likely in case of nitriding process, because there is no quenching is occurring here. That is why the cracking and distortions are less likely. Hardness is retained at a very high temperatures. Up to 500 degrees centigrade, the surface hardness can be retained, whereas in carburizing it is only up to 200 degrees centigrade. The main disadvantage, the longer duration and smaller depth of strengthened layer. This is the main disadvantage. That is why many times in industry, nitriding is not preferred. Here you can see this is a carbonitriding process, where after initial preheating, basically both carburizing gas and ammonia are given, and this environment induces both carbon and nitrogen to create the surface hardness, and after that quenching is done. That means basically it is a carburizing process, and only extra thing is that some amount of nitrogen is added. So carbonitriding is a modification of the carburizing process. It is not a nitriding process, that you have to remember. Ammonia into the carburizing atmosphere so that some nitrogen can get into the surface. Okay, so lower temperature than carburizing, okay, because nitrogen helps in diffusing the carbon into the material, 700 to 900 degrees centigrade, and the shallower depth if you compare with respect to the carburizing depth, okay, and the shorter time than the carburizing process. So here you can see the depth of the carbon and the nitrogen in case of a carbonitriding process. Here you can see a comparison of the different processes that we have discussed. Like nitriding, you can see up to a very small depth it is a very high hardness produced. In case of carburizing, you can see up to a larger depth the hardness is good. In case of induction hardening, initially the hardness is small, but up to a very long depth it can maintain a good hardness when that requirement is there. Okay, and volume hardening is the general hardening process through which the material is hard. Okay, thank you.